This video will review calculations that involve pH for both strong acids and then just introduce the difference in calculating pH, strong acids versus weak acids. But there's a completely separate video on how to calculate pH for weak acids because they're a lot more challenging. I first want to remind you of the key difference between strong acids and weak acids. Strong acids are acids that completely dissociate into the individual ions when they're added to water. And weak acids partially dissociate. So when you put them in water, you're going to see some hydronium ion, but the majority of a weak acid stays intact, okay, as the original weak acid. And obviously that's going to affect calculations of pH because, as you will see, if you don't already remember, the formula for pH is minus log of the concentration of the hydronium ion. And so since a weak acid doesn't make very many hydronium ions, the pH calculation is totally different. And I also want to emphasize at this point that you not confuse the terms strong acid versus weak acid with concentrated versus dilute, okay? That's an important distinction. So, for example, let's say that I gave you a pH of 1, which is very acidic, right? Would you be able to say anything about whether or not that solution of acid came from a strong acid or a weak acid? The answer is no. You know nothing about the strength of the original acid. You only know what the concentration of hydronium ion is, okay? I could get a pH 1 solution by adding just a little bit of a strong acid, or I could dump in a whole bunch of a weak acid and get the same concentration. So just be aware of these two seemingly similar definitions. All right. In an aqueous solution, which is what we're working with here, the product of hydronium ion, concentration of hydronium ion, times the concentration of the hydroxide ion is a constant at a particular temperature. So you may decrease the concentration of hydronium, let's say, in a solution by doing a number of things. But at the same time, if that happens, then the concentration of hydroxide must increase. Okay, so hydronium ion and hydroxide ion are inversely proportional. Sorry about that. As one goes up, the other has to go down since their product equals a constant. And if the concentrations of these two ions are equal to one another, it is a neutral solution. If the hydronium ions are present in a larger concentration than the hydroxide, it is an acidic solution. And if the hydroxide ions are present in a higher concentration than hydronium, it is a basic solution. All right, so here again is the official formula for calculating pH. Just a couple slide brief history on where pH is 7 being neutral, where that comes from, and where the whole kind of background of pH comes from. It turns out that even in pure water, you have some hydronium and hydroxide ions present. Not very many, but you do have some. And that's due to what we call the autoionization of water, which you can see how it occurs with these red arrow mechanisms, curved arrow mechanisms. Again, it's a very low concentration, but even in neutral water, there is some. All right, so remember I said a minute ago that the product of the concentrations of hydronium and hydroxide ion equal a constant. Well, at 25 degrees C, which is simply room temperature, the product equals 1 times 10 to the minus 14. In pure water, these concentrations are equal to each other. So just doing some simple math, that means the concentration of each of these ions in pure water is 1 times 10 to the minus 7. So if you plug this value, 1 times 10 to the minus 7, into the formula for pH, guess what? You get the pH of pure water at 25 degrees, I should clarify, is 7. And that's where the pH 7 comes from. It is the actual representation of the concentration of hydronium ion in pure water. And just to kind of familiarize yourself or refamiliarize yourself with the pH scale, I think typically textbooks teach that pH goes from 0 to 14 or 1 to 14. I just want to point out that the pH scale can be above 14 and below 0. If it's below 0, it just means it's a very strongly acidic solution, okay? And another feature of the fact that the concentration of hydronium ion times the concentration of hydroxide ion equals a constant, okay? So that's what makes them inversely proportional to each other, right? As one goes up, the other has to go down. So if you look at this chart, table, look at the product of hydronium ion times hydroxide. And by the way, if you don't remember this, H3O plus, the hydronium ion, is often simply written out of simplicity, laziness, whatever, as just H plus ion. They're considered equivalent so that it doesn't confuse you. So, for example, if we find that the concentration of hydronium ion in a solution is simply 1, that means that the concentration of hydroxide is 1 times 10 to the minus 14. So you can see as you decrease the decrease the concentration of hydronium ion, what happens to the concentration of hydroxide? It goes up. And so the product at any point of hydronium times hydroxide is always 1 times 10 to the minus 14. Okay? At least at 25 degrees, right? So this is kind of a handy little relationship to remember. I love this chart. This PowerPoint is pretty simple. It's just a bunch of plug and chunk calculations that have to do with pH. Some problems will ask you for pH, some will ask for pOH, some will ask for the concentration of hydroxide, and some for the concentration of hydrogen ion, which, as I just said a minute ago, should be considered equivalent to the concentration of hydronium. And you can get, like if I gave you, let's say, the pOH of a solution and asked you to find hydronium ion concentration, there are 2 routes to follow to get that answer. One would be to go counterclockwise. In other words, you'd find the concentration of hydroxide first and then the concentration of hydronium. Or you could go the other way. From pOH, you could find pH, and then from pH, find hydronium ion concentration. So this is a really handy chart. You might want to jot it down or download it. It gives you the formulas in each case, how to get from one value to the next. And this is really, in a quick view, what we'll be going over in this PowerPoint. Let's do some practice. And I always tell students that the most challenging part of all these pH calculations is learning how to use your calculator readily instead of waiting for a test to know where all the buttons are. So here's a simple one. What's the pH of these solutions? And is the solution acidic or basic? Okay, remember, acidic solutions have pH less than 7. Basic solutions have pH greater than 7. All right, so these are just simply plug in. Remember the formula. pH equals minus log of the concentration of hydronium, which in this case is 1 times 10 to the minus 2. If you plug that into your formula, into your calculator, you will get that pH equals 2. That is an acidic solution, right? Any pH less than 7 is acidic. Let's do this one. All right, so pH in this case would be minus log concentration of 1 times 10 to the minus 12 plugging that into your calculator, you would get that pH in this case is 12, and that is basic. So I want to point out something else that simplifies your life in some cases, if you haven't already noticed it. The log scale, you may not remember this from math, the log scale is simply used, it simply represents the exponent in some type of number, okay? So notice in this case, the pH of 2, there was an exponent of 2. When the pH was 12, there was an exponent of 12, okay? Because that's what log does. It takes the exponent. So you'll notice the log scale is used when you're dealing with either very small numbers or very large numbers. In the case of pH, it's very small numbers. And it's just cumbersome to be writing out that scientific notation all the time, so we use the log scale. Just remember that there is a minus in front of the log, all right? So whatever the exponent is, it's going to be the opposite sign of that. And another thing I'll point out, if the coefficient in the scientific notation is exactly 1, you can literally just take that exponent and change the sign. Okay? Again, if the coefficient in scientific notation is exactly 1, you can literally just take the exponent and change the sign to get pH. If this coefficient is anything other than 1, you're going to have to plug it into your calculator to get a good answer. All right, so we're moving along on that little square of formulas and calculations a couple slides ago. So let's go backwards. Okay, we know that pH equals minus log of the concentration of hydronium ion. So what if I gave you pH and asked you to find the concentration of hydronium ion? How do you get the inverse of log? Do you remember how to undo log? Since this is log, log base 10, you're going to use 10 raised to the power of the minus pH. Again, don't forget that minus sign. It's not just a simple log. They threw in a minus sign there. All right, so find what you want to find on your calculator is the 10 to the x button. And again, remember to put the negative in for this formula. So let's look at some of them. If pH is 7, okay, so we want to then say concentration of hydronium ion is 10 raised to the minus pH. pH is 7, so 10 raised to the minus 7. The more common way to show this is with a coefficient, 1 times 10 to the minus 7. All right, so go through, do a couple of them, make sure that you're doing it correctly. So again, if the pH is 4, that means the hydronium ion concentration is 1 times 10 to the minus 4. 13, again, 1 times 10 to the minus 13. You can see the pattern, hopefully. Now, if the pH has a decimal in it, so it's not quite as easy to go from pH to hydronium ion concentration, what you would enter in your calculator is 10 to the minus 3.4, but you don't want to leave it like that, okay? Most people can't wrap their head around that, and that is not considered the most simplified form. And so if you put 10 raised to the minus 3.4 in your calculator, you should get 4 times 10 to the minus 4, which makes sense, right? Look, 3.4 is between 3 and 4 as far as an exponent, and there you go. All right, so we said this earlier, that in any neutral water, so pure water is obviously neutral, the hydronium ion concentration will equal the hydroxide ion concentration, and that at 25 degrees Celsius, which is the temperature, it's room temperature, most time we'll be dealing with that, each of these ion concentrations are 1 times 10 to the minus 7, or another way to say that is the product of both of the ions in a neutral solution at 25 degrees is 1 times 10 to the minus 14. We've also talked about the inverse relationship between the two ions, okay? So as we increase the concentration of hydronium, for example, the concentration of hydroxide must go down because the product is a constant. So now let's go from concentration of one of these ions, let's say hydronium ion, to the concentration of hydroxide. So what is the relationship between the two? Let's look at it again. The product of both ions is 1 times 10 to the minus 14 molar. Well, no, not molar. Molar squared, but we're going to leave that out. We treat that as unitless at this point. So if I asked you to figure out the concentration of hydroxide, how would you rearrange this formula? All right, so you can easily find the concentration of one of these ions if you have the concentration of the other one. You just have to remember that 1 times 10 to the minus 14th always goes on top, divide by the other one. So let's solve this problem they're giving us right here. If hydronium ion equals 1 times 10 to the minus 1, what is the hydroxide? Let's go ahead and plug in the values. So in your calculator, it'd be 1 times 10 to the minus 14. The given concentration of hydronium ion is 1 times 10 to the minus 1. And when you plug that into your calculator, or if you can do mental math, it is pretty clear that the answer to that then is 1 times 10 to the minus 13 molarity is the concentration of the hydroxide ion in this solution. All right, let's go the other way. So you can see now that all these are pretty simple plug and chug, but do a bunch of them. Just do a bunch of practice ones just to get the wheel greased in your head so that if you're on a quiz or a test, you're not kind of struggling trying to remember. So in this case, they're giving us hydroxide and asking us for hydronium. So I'm going to rearrange that formula to look like this. Remember, the 1 times 10 to the minus 14 is always on the top here for those of you who maybe not like algebra. All right, so let's go ahead and plug in the value. 1 times 10 to the minus 14 divided by the given concentration of hydroxide. I've mentioned a couple of times that at 25 degrees Celsius room temperature, the product of hydronium ion concentration and hydroxide ion concentration is 1 times 10 to the minus 14th. I apologize for my dogs. And so in a neutral solution, these two concentrations are equal to each other and equal to 1 times 10 to the minus 7 molar. Well, it turns out if you change the temperature, the product of these two also changes. So see that it's a little bit larger, 2.5 times 10 to the minus 14th. And being a little bit larger means you get a little bit more of ionization as the temperature increases. What does that mean? Well, that means now that the individual concentrations of hydronium and hydroxide at 37 degrees is not 1 times 10 to the 7. It's the square root of 2.5 times 10 to the minus 14, whatever that is. But I do want to emphasize that it is still a neutral solution. As long as the concentration of hydronium ion equals the concentration of hydroxide, regardless of what their individual values are, when they equal each other, that is neutral. But neutral isn't always pH 7. Neutral is pH 7 only at 25 degrees Celsius. As we raise the temperature, there's going to be more ions, which means the pH is going to be lower. So in this case, if you take the square root of 2.5 times 10 to the minus 14, you get that each individual concentration is 1.58 times 10 to the minus 7. So the concentration of each of the ions has increased at this higher temperature. So now let's figure out what pH is at this temperature. Remember, pH is minus log of the concentration of the hydronium ion. So if we take log of 1.58 times 10 to the minus 7, we get that the pH of this neutral solution is 6.8 at a higher temperature. Kind of weird, but interesting. So this is a reminder to make sure you memorize the handful of strong acids and strong bases. Every other acid or base, if it's not on this list, is a weak acid or base. And you'll see in the next PowerPoint that the way we find pH is completely different depending on whether or not it's a strong acid base or a weak acid base. That is my dog chewing a squeaker toy. Anyway, make sure you commit these to memory. Up until now, you have been dealing directly with the concentration of hydronium ion in trying to calculate pH, pOH, etc. But in reality, most of the time, you're not going to be given the concentration of hydronium ion. You are going to be given the concentration of the actual acid that is used to make an aqueous solution. And so you have got to be able to figure out what is the concentration of hydronium ion that this particular acid will create. It's easy for a strong acid or strong base because 100% of it ionizes, or dissociates to form the hydronium ion and the conjugate base. The original intact acid is all gone, and whatever the original concentration of the acid was will be the concentration of the hydronium ion. And as a matter of fact, it will also be the concentration of the conjugate base, since the stoichiometry is all 1 to 1 to 1. Here's a very simple example of a typical pH problem. What is the pH of 0.01 molar HCl? So the first question you should ask yourself on pretty much every question on this next exam is this a strong acid or a weak acid? And hopefully you'll have them memorized then. That is a strong acid. And so it 100% dissociates in water to give the hydronium ion and the conjugate base. Sorry about that. And so we started out at 0.01 molar hydrochloric acid. And because of the stoichiometry, we're going to make 100% of that's going to be converted so that we end up with 0.01 molar hydronium ion. And so now define the pH just like normal. pH equals minus log of the concentration of hydronium ion, which is 0.01. And so the pH of that is 2. Okay, so practice a couple more if you want, if you haven't gotten enough practice calculating pH. I like to do these in my head if the coefficient is 1. I simply write them in scientific format. Take the exponent, which is 4, change the sign, and so the second one has a pH of 4. 12 molar. Plug that into your calculator just to register in your brain that you can have negative pHs. So it turns out that minus log of 12 is actually around -1. So you can have negative pHs. They're just very, very, very strongly acidic solution. We really haven't worked many examples with a base, so I want to make sure you have some experience with them. You should also make sure you practice pH problems with bases. So we're just going to call BOH a generic base. So a strong base is one that's going to dissociate 100% into the hydroxide and the conjugate acid. So sodium hydroxide is a very common strong base. Now you may notice that in most base dissociation reactions, because water doesn't really actively participate in the balancing, a lot of chemists will just put H2O over the arrow so that they don't have to worry about balancing the atoms in water. All right, so these are all strong bases. But what you need to be a little bit careful of, there are actually acids that have 2 acidic hydrogen to donate 2. For example, H2SO4 would be one. But it's pretty common with bases, let's say barium hydroxide. If you were to write the ionization reaction of barium hydroxide and balance it correctly, you would see that there are 2 hydroxide ions formed from every one original barium hydroxide. So you have to be careful of that stoichiometry when you're calculating pH. So if I had a 1.0 molar solution of barium hydroxide, I would end up with a 2 molar hydroxide solution. So that's obviously going to affect the pH. Here are some simple examples. Again, when I'm doing pH and pOH, I'd like to write the values in scientific notation because then I can quickly see that the pOH of this, you can plug it into your calculator if you want, but I can see right here that the exponent is 2, -2, and I can just bring that straight down because the coefficient is 1. And so the pOH, be careful because this isn't pH, this is pOH, is 2. So to find pH, you need to remember the relationship that pH and pOH when added together equal 14. And so if pOH equals 2, that means that pH is 12. I'll do one more for you real quick. All right, so if the concentration of hydroxide is 1 times 10 to the minus 4, that means that pOH is 4, which means that pH equals 14 minus 4, or 10. And the 6 molar NaOH, again, just to show you that pH can go higher than 14. This is a perfect example. If you have a 6 molar strong acid solution, you're going to get a pH of 14.8. So we've talked extensively about finding the pH of strong acid and strong base solutions. What if an acid or a base you're given is a weak acid or base, which simply means it doesn't dissociate 100%? If the weak acid or base does not dissociate 100%, how much does it dissociate? And how do we know how much hydronium ion or hydroxide ion that weak acid or base will form? We need more information, right? You can be given the initial concentration, the weak acid or base, but until you know the extent of ionization, you're not going to know how much hydronium ion you've made. As a matter of fact, and this shocked me when I first learned it, less than 1% of the original weak acid in acetic acid dissociates or ionizes to form hydronium ion and the conjugate base. So the vast, vast majority of a weak acid, in this case acetic acid, greater than 99% of it, remains intact, okay, without having donated a hydrogen ion. Now this is in water. Obviously, if you put acetic acid in the presence of base, you're going to get more than 1% that converts. And just as a side note, if any compounds you see that end in COOH, which is sometimes condensed to CO2H, same thing, these are all weak acids. Okay, they're called carboxylic acids. You'll hear that if you take organic, but just kind of heads up, they're all weak acids. So anyway, to kind of visualize on a molecular level a weak acid, we would say that this reaction lies far to the left, which means that reactants are favored. And sometimes that's shown with the arrow going to the left longer than the arrow going toward product. It turns out that every single weak acid and weak base has its own unique percent of ionization or dissociation in water. What we need to be able to do is need to be able to find out is the percent ionization, how much of it's going to ionize. And that means that we need to handle on the concentration of hydronium ion, concentration of fluoride ion, and the concentration of the original intact acid, in this case hydrogen fluoride. And when we know the balance of these three species, we can predict the percentage ionization. Chemists use a constant called Ka. It's actually a type of equilibrium constant, which we'll get into much more in the next unit. It's also frequently called acid ionization constant for obvious reasons. This little subscript A just stands for acid. But take a look at the generic chemical equation shown at the top and then compare that to the expression for Ka. Notice that in the numerator of Ka are the products. So I'm going to kind of simplify this. So Ka can be thought of the concentration of products on the top divided by, you see what HA is? Divided by a concentration of reactants. So it's products over reactants. So the more a weak acid or a weak base ionizes or dissociates, the larger the Ka will be. Notice also that water has been left out of the equilibrium expression, and that's because the concentration of water is a constant. It doesn't change. It does have a value, I think it's like 55 molar, but it doesn't change. So the concentration of water is lumped into this constant value, Ka. But the most important thing I want you to understand right now is that the larger Ka, the more acidic the acid is, the more likely it will be to ionize. And we'll pick up calculating the pH for weak acids and weak bases in the next PowerPoint.